Okay, Bismillah ar-Rahman ar-Rahim. Today I'll discuss complex frequency and related topics. So, as you recall, signal Vm equal to A cos omega t plus theta. So this is the normal signal, and this signal has an amplitude and a frequency, so we can just describe it like this, as V of t is equal to A cos omega t, where A is the big value, okay, and omega is 2 by f. So this is the normal signal here, and we can get its phasor representation as A and the angle theta, so A theta. Now, in frequency domain analysis, let's say we have a simple circuit where we have S, R, and L, and we have a V here, that is your VI. This is R, that is L, and we like to find what is the current I here. So we can use the S-domain analysis. So this becomes SL, and that is R, and we can say that I is equal to VI divided by R plus SL equal to A angle theta divided by R plus SL. Now we know that S equal to J omega. So if we know what is omega, then we can tell what is S, and we can substitute here the values, and we get the current, right? So let's say the current is X, and the angle is phi. The angle is phi. Okay? So we have only the change in the amplitude and the angle. So we can write the current in time domain. I of t is equal to X cos omega t plus phi, which is the new angle. Okay? So this is in simple frequency using the S-domain analysis. Now, in some applications, we have the signal has a damping factor. So the signal is V of t is equal to A, let's say, E to sigma t cos omega t plus theta. So that is the input voltage, let's say, or the input signal. Now sigma is called the damping factor. So this is sigma is damping factor. So as you can see, it is exponential decaying function. Sigma should be less than 0, so it should be negative. Otherwise, it will be going up as t goes to infinity. This will go to infinity. So it will goes up. It is an unstable system. So sigma should be less than 0. Now again here, if I want to do the phasor representation, I can say V equal to A angle theta. Now this, you remember, it is from the previous example, it is for only this without E to sigma t. So how to distinguish between this and this? The two signals, if we have a damping or without damping in S. Now S, since we have sigma, S, the new S is, S will be sigma plus J omega. It is not J omega anymore. It is sigma plus J omega. Now let's take just a simple example. If V of t is equal to 4 e2 minus 2t cos 40 plus 45, let's say this is my input signal, and I want to find I of t for the circuit. Let's say we have the following circuit, right? The following circuit. So we have this is V R S L. This is 1 over S C. So again, V here will be 4. The angle is 45. But we have to make sure that S is, in this case, minus 2 plus J4. So this is the only change now. In phasor representation, the amplitude is the same, phase is the same. The only change is S. So S is minus 2 plus J4. So to find the current, then we can say I is equal to 4 angle 45 divided by R plus SL plus 1 over SSE. Now we can manipulate this, right? And then the only thing you have to change is that S should be now should be minus 2 plus J4, huh? Because 4 is omega, minus 2 is the damping factor, which is this, right? Sigma. And then you can find your expression. So let's say you got the expression as whatever it is. So let's say it becomes X with Zawiya phi again, right? Then we can say I of t is equal to X e2 minus 2t cos 4t plus the angle, which is the new angle, that is phi. So this is the only difference now. So you can see this is your time domain representation. So to just summarize, when we have a damping sigma with a damping factor, that's sigma, and sigma should be negative, less than 0, so that you have a decaying function, otherwise it will be unstable. Then the only thing we have to do in frequency domain analysis, we have to replace S by sigma plus j omega. And then use this to substitute it here and do the same as you have done with the normal frequency. So that is regarding the complex frequency. Now, the second part here is poles and zero and their locations. Let's say poles and zero. Poles and zeros. Let's say we have a transfer function, h of s equal to s into s plus 1 over s minus 2 or plus 2 into s plus 3, right? So this is a transfer function. We have 0 at s equal to 0, and pole at s equal to 0 at s equal minus 1, pole at s equal minus 2, pole at s equal to minus 3. Now if I will sketch this in the s plane, that's sigma, that is j omega here. So we have 0, usually the 0 will be circle, right? So the 0 is the circle. So we have a 0 at 0, and we have a 0 at minus 1. So this is minus 1, this 0. So we have two zeros here. Then we have poles. So the poles, we have one pole at s equal to minus 2. But keep that handy. You know, the standard form is s minus z over s minus b. So you have to say minus 2, that will be plus, right? Yani, I can write this as this. I can write this as s into s minus 1, huh? Okay? So you can see that is the first one. Over s minus 2, s minus 3, right? So you can see we have minus 3 and minus 2. So the poles here will be at minus 2, so this is the first one. Let's say this is minus 2, and we have another one at minus 3. So these are the locations of the poles. Any pole here, it means sigma is positive, right? Then it means that your system is unstable. So the poles should be to the left side of the instrument. Should be here, right? If it is there, it means it is unstable. And we have to do something about it. So it should be here. Now in this, as you can see here, you have the poles are distinct and real, but they can be conjugate. يعني ممكن يحصل ايش عندنا poles like this, one here and one here. So this is a complex conjugate. يعني when there is an imaginary number here, then it can be complex conjugate. And now we have this, and we can have also balls that they are on top of each other, يعني at the same place. They have, يعني ممكن this can be s minus 2 square, right? So we have what we call it repeated balls. So we have two distinct balls, and we have repeated balls here, right? So the name, and we have a complex conjugate balls. Now, based on these three, it means we have three cases. We have underdamped, overdamped, and critically damped. Based on this, right? So depends on your balls, you'll have the stability. Now it is stable, lacking based on underdamped behavior, or critically damped, or it is overdamped. So based on the balls now, if they are distinct and real, if they are real and repeated, if they are a complex conjugate. So we have three different cases. Now, from the transfer function, the natural response, actually, we have to use the natural response only for the balls to tell if it is underdamped, overdamped, critically damped. So you have to look all the time at the denominator of the transfer function, which is the response. As we said, the natural response is fixed. You take V out from the capacitor side, or from the, if you take the output, as we said before, let's say this is your circuit, right? And that is VI here. So we can take VL, VR, VC. So if we take VC over VI, the denominator will be the same. VL over VI, the denominator will be the same. VR over VI, the denominator will be the same. And that is actually the natural response. So we have to look at the natural response to identify the behavior of our system, if it is underdamped, overdamped, or critically damped. So let's just take a simple example where we have h of s for the filter, let's say, which is s, just an example, s squared plus omega naught over q times s plus omega naught squared. So this is the transfer function of a filter or a resonator, let's say, or whatever it is. And now we have to tell if this is the behavior here, first, it is stable or unstable, it is underdamped, overdamped, or critically damped. So we have to solve this. So we know that this is a quadratic equation, and we can find S1 and S2 as minus B, which is minus omega naught over Q, plus or minus square root of B squared, which is omega naught over Q squared, minus 4AC, which is 4 omega naught squared, divided by 2A. I don't care about the 2A. I have to worry about this, huh? Because 2A will be just you define. I have to worry about this now to tell. طبعا to find the balls I have to define 2A. I have to define. So this is 2A, which is 2. لكن I don't care about this. Okay, let's just consider this. Minus omega naught over 2Q plus or minus 1 over 2 square root of omega naught over Q squared minus 4 omega naught squared. Okay? So these are the two balls here, S1 and S2. You can see that if this term equal to 0, right, then we have repeated balls minus omega naught over 2Q plus or minus 0. So we say two balls at the same place. If omega naught over Q is greater than 4 omega naught square, this number will be a real number, and we'll have two distinct balls. واحد minus omega naught over 2Q plus ثاني minus omega naught over 2Q minus. So we have two distinct rules. And finally, the third one, if omega naught over Q square is less than 4 omega naught square, then this term will be less than this term, and this part will be an imaginary number. So we have J, and that will give me the complex conjugate balls. So we have two balls in complex conjugate. So based on this, I can tell now if my system is having two exact roots or repeated balls, two repeated balls, or two distinct real balls, or two complex conjugate balls. And based on this, I'll know if it is under damped, over damped, or critically damped. So we have these three cases. Now, as you can see here, you have to look at them, right? You have to look. Now, under damped, critically damped, over damped, it depends on the bulls themselves, if they are repeated, right? So we have, as we said before, we can have two bulls, they are distinct, right? We have two bulls, they are repeated, right? So same place here. And we may have two bulls, they are in conjugate, right? So let me just change the color, so to make it green. So that is conjugate here, right? So we have three cases. We have repeated bulls, complex conjugate, and distinct. And depends on these bulls, we can tell if it is under damped, over damped, or critically damped. So for just a minute here, I have to just give you the so if the roots, this is over damped here. So over damped, if you have the roots are the same and distinct, sorry, they are distinct root, and this will be under damped. So if we have conjugate, and this will give you critically damped. So you can see if the two roots are conjugates, right, then we have under damped. If they are distinct, we have over damped. And if they are the same, repeated, right? If they are repeated, equal roots, we say that is critically damped. This is this one, this one. So we have critically damped. So we have over damped, that is the complex conjugate. Sorry, under damped. Over damped, they are distinct, and critically damped, they are repeated roots. And you can use this. And here we can see one note here. If you look at Q here, then we can use Q as a control component. I mean, we can increase Q or reduce Q to make this part they are equal or less or greater, to make this part of the equation. So we can make it 0 using Q. No, I said omega naught, we cannot play with it, right? So we can use Q. So if we increase or decrease Q, we can make this equal or less or greater, positive or negative quantity. So we can make this using Q. We can make this term 0 or positive or negative, so that we can have the different situations here. Okay, so this is for the bulls on zero locations, and if the system is damped, under damped, critically damped, or over damped. So this is the things we have to worry about in this situation.